All right, so it's just a whole series of events today. During my first class, my internet went out about 90 minutes in and has just been going in and out since. It's been stable for 10 minutes, so I'm knocking on wood that it's going to keep staying stable, but we'll find out. So I sent out an email about that. If you didn't see it, that's fine. If you did, well, you're still here. Also, it's telling me now that there's a waiting room and I have to admit students. I've never had to do that. I never changed any settings, but Zoom clearly likes to change settings without my permission since it, changed my recording setting a couple classes ago. Either way. All right, let's get to it. First of all, reminder that we have 4.6 homework due today, then 5.3 and 6.1 due on the 30th. Test 3 has already occurred. So you had Friday, Saturday, Sunday, Monday to do it. You had 4 days. I told you several times about that. So hopefully we all got those done. I know I saw some results. I saw the results yesterday, about halfway through Monday, but I haven't looked since then. And I think I still had 1 or 2 people that needed to take it at that point. So hopefully you did, because we're not going to make any exceptions for that rule. But the results I saw at that point were really good. I gave you 2 attempts and nobody had taken a second attempt yet, at least. I don't know if anyone did after the fact, but again, grades were all A's and B's for the most part from what I remember seeing. So you're probably happy at that point. The final, next class. So we will not be teaching, I will not be teaching next class. We will not hold regular class next time because you'll be testing. So this is it for our meetings. Sad day. So that's this Thursday. There will be no exceptions to this. So if you missed the final, you missed the final, because I have to put my grades in Friday morning. Then in SIS, you should be able to see your grades either Friday evening or maybe Saturday or Monday. I don't know if they actually do any uploading processing over the weekend or not, but I'll have my grades in Friday morning. So hopefully you'll be able to see them Friday afternoon. Again, I've never been quoted how long it actually takes SIS to process and post once I've posted. Don't email me asking for your final grades because I don't give out final grades over email. It's just you got to go to SIS to see your A, B, C, D, or F grade. So the final, you're only going to get 1 attempt, which shouldn't matter. Most everybody's only been using 1 attempt anyways. To review for the final, you have test 1 through 3 reviews, as well as the tests. The reviews and the tests were similar. The last review had a little more questions versus the test, but that's not a bad thing, I don't think. If you see a second question that's like the first one and you felt good with the first one, you can just skip it because the reviews aren't graded. But then I also provided a few extra problems. So in my math lab under your assignments, I believe that's under the 6.1 homework. It should say something like review 4. I don't remember exactly what I titled it. And I did post that. I want to say it's about 10 to 12 questions, so nothing crazy. And that just covered the last 3 or 4 sections that were not covered on the first 3 tests. So all of the tests are 20%. Test 1, Test 2, Test 3, and the final are 20% each. Your homework is 20%. Remember that any homework grade that's a 90 or less, I'll add 10 points to it. Any grade between a 90 and 100, I'll just make a 100. So you're not going to have any homework grades that are above 100. Please remember that my math lab, calculating your average is pretty much trash. You need to calculate your own averages. You're calculus students. You should be capable of that. Take all your homeworks, add them up, divide by the number of homeworks. There's your homework average. If you want to go ahead and add your 1 to 10 points into the assignments that you should get those added to, then go ahead and do that, but you will have to do it manually. So then you'll have your homework average. Once you have that, take your 3 tests and add it to the homework average. Divide by 4, that's your current average. Because all of those are weighted the same. Homeworks are weighted the same as the tests, the way it worked out. I prefer having 4 tests in this class, but summer and online and with this format, I just couldn't do 4 tests and a final. It was impossible. I tried, but we didn't make it there. And that's okay. I'm sure you feel okay with it. The final exam is supposed to be no notes, no books. You're allowed a calculator. Feel free to use those. It's supposed to be your own work. Cheating will not be tolerated, and you will have a place in Canvas to submit your work. partial credit, any partial credit. And remember, if you see something that you think you deserve partial credit for, it's in your best interest to email me and say, hey, Mr. Beckner, check out my work for problem number 17 or problem number 4, whatever. So make sure to submit your work in Canvas. Remember, I have the right to deduct as many points as I want if you don't submit any work, because this is calculus. There are not a lot of problems that you can do without showing your work. Yes, some of the basic integrals or derivatives you could probably do in your head and just write down the answers. But most of these problems are a little more involved. You'll have some that are short, but you're also going to have some that are more involved, just like the regular tests. So if you have any questions about this, let me know during class or shoot me an email. Yeah, so in terms of what's going to be on the final, nothing covered today will be on the final exam. Nothing that we cover today will be on the final exam. I'm just going to kind of pick and choose a couple of topics and just as extra knowledge. And I'm going to pull from 5.7 and 6.2, I think. I was kind of playing around with the idea of doing something specific with economics, but honestly, I would rather just dive into more calculus concepts, actually show where the idea of exponential growth comes from as what we call a differential equation, and also introduce you to the idea of taking derivatives when there are multiple variables, but you don't have to use implicit differentiation. It's kind of a fascinating field, and it leads to really cool mathematics in 3 dimensions when you only really need to consider 2 dimensions in an argument or something like that, as well as all sorts of other crazy things that we don't need to get into. So let's do a new document, and this will be 5.7 differential equations. I also don't know that I'll take the full 2 hours to discuss this stuff. I really would just want to give a blanket approach to this, to these ideas, and show you what they can, or how they can be used. So differential equations. We have been dealing with these, believe it or not, without knowing it, but they are already set up for success. We dealt with these when we were covering integration by parts. When we were doing the whole, as well as substitution, in fact, but integration by parts is the bigger one. So when we were doing integration by parts, we would say let u equal this, and then dv was the rest. So it was the let dv equal blah, 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 dx bit. And then what we did is we integrated it. The dv equals the integral of blah dx. And what we would have is the left side was just this. And I mean, the basic idea is that there's a 1 here, and the integral of 1 is the variable. Good Lord. I don't know what just happened, but my house just shook. Sorry, the distractions today are insane. The world is, I don't know what's happening. Distractions, okay. So whatever this d is, if you're just integrating a constant, that means you get that variable. If you were integrating v dv, you get v squared over 2. So it's saying, hey, this should be integrating with v's, so you get v. And then this blah, I mean, you get whatever, the integral of the blah, but it's in terms of x's. So if this was originally, say, in, let's say it was x cubed, then this would be x to the 4th over 4, and you'd have your plus c if we weren't doing a definite integral. And you'd be solve for v. That was a differential equation. We call a differential equation because it's an equation that you have differentials in, and the goal is to integrate. Go ahead and get some spacing. That'll be enough. So that was a differential equation. Differential equation is one in which the differentials, the dx and the dv, are separated and integrated. And then you integrate. variable to. Generally, we use what is known as separation of variables. Separation of variables means that you want anything that has, say, a v on one side and anything that has an x on the other side. Now, the differential equations we ended up setting up under integration by parts were actually pretty simple because you generally only had one variable. So you'd have your x's and your dx's on one side. You actually had to multiply. I'm sorry. Let me stop what I was about to say. Let me stop what I was about to say. So you would have dv over dx, and then you'd multiply both sides by dx. That was us separating the variables. If you went one way, if you had, say, a derivative, that was us separating us. That's not related to what we just wrote, though. So if you had dv over dx equals 5, multiplying by both sides by dx is an idea of separating the variables to get the v's on one side and the x's on the other. When you're using integration by parts, we're already set up as a separation, though. That you already have no real v's except it's differential on one side and then all the x's on the other because of the way you did a substitution. But they're not always that way. Very often, a differential equation is set up as a derivative equal to something that you must separate and integrate. Now, the actual math behind separation of separation of variables can be mind-boggling for problems not in our course. Ours are going to be very easy, and we will see that. Differential equations are all over the world. A lot of things react in terms of a growth rate or decay rate. For instance, when you want to talk about a medium timescale model for the population of America, is to say that the growth rate, population growth rate, is proportional to the population. I say medium time scale. A short time scale, we just say population is growing proportionally. So it's increasing 5% every year, 10% every year, something like that, the actual population. But that only works for like 5, 10, maybe 20, maybe 30 years. Eventually, you start seeing the population kind of break out from linear growth and they start growing quicker and quicker. Or slower and slower, depending on where you are in the ultimate grand scheme of things, of what we call the logistical model. So a medium time scale that's usually good for maybe 100 or 200 years, roughly, maybe 100, 200's pushing it, let's just say 100 years, is to say this, that instead of just saying that the population increases at a constant rate every year, we say that the population growth rate, which is a derivative, is proportional to the population. And that statement, I think that makes a lot of sense if you actually think about it. Our size should be growing based on our size. The more people there are, the more quicker we're going to grow. Again, as a basic idea. When you say something's proportional, the idea is it's just a k, a constant, times the variable. So like if we say y equals kx, that means that y is proportional to x. But we're not saying y is proportional to x. We're saying that a growth rate is proportional to x. So here's what we're going to do. Let's call population y, so that's in people, and the time in years, t. Instead of doing x and y, let's do y and t, because they're just better associations. You don't want to use x and t, you can, but we're going to go with y. So If something's proportional, that means you just take that variable and multiply it by a k, where k is a constant. So the population growth rate, this population growth rate is the rate of change of the population compared to time, the rate of change of time. The rate of change of people is dy. So the rate of change of the population is dy. That's that differential. The rate of change of time is dt. So we're saying dy over dt. And a lot of people don't think about those separately. They just say, all right, we're going to end up solving for y, so y is the dependent variable at the top. The independent variable is time. The people are based on how much time has gone by, so dy dt. That's another way to think about that. So we're proportional. So this next bit is just k times a variable, and we're proportional not to how long things have gone on. So it's not kt, it is not this. It is actually proportional to the number of people. It's growing proportional to the population, which is y. Now this is nothing like what we saw under integration by parts. The integration by parts, the right side, they always had the same variables, x's and x's, t's and t's, whatever. This is not going to be that way because we're going to need to separate the dt. You're going to have a dt over here next to the y. So if you try and treat this like the process of integration by parts, you still multiply both sides by dt. To separate your differentials. So you go dt, and then dt times dy over dt equals ky times dt. So the dt's cancel. And what we end up with is dy equals ky t. And you might say, well, go ahead and integrate. I'm going to do blue temporarily for wrong. If you integrate this, you can't integrate. I'm going to erase this in just a second. A few seconds. The reason you can't integrate, I missed my dt. I wrote a t instead of dt there. That was supposed to be dt. Because it was k times y times the dt. You can't integrate this because this y, that's our variable. Remember, k is just a number. K is 3 or 5 or 1/2, whatever. The variable does not match the differential. You can't integrate this. So you can't integrate it. So what you have to do instead is you have to separate the variables. You've got y's on the right side and on the left side. You want to move this y over to the other side somehow. It's being multiplied by a bunch of stuff. So to do that, you got to divide it. We divide by y to separate. So divide by y, divide by y. And these do not cancel on the left. They cancel on the right, but that's dy and y. Remember, dy is its own thing. So what we now have is dy over y is equal to k dt. And this is integrable. We can integrate this because there's only y's on the left side and it's in a form we understand. And there's only a dt on the right side. Remember, this k is just a number. So now we integrate. So we get the integral of dy over y equals the integral of k times dt. I'm even going to pull the k out just to emphasize that it's a constant, it's a number, it's unaffected. So it's the integral of dy over y equals k times the integral of dt. There's no real variables in this integral, so when you integrate a constant, you just get the variable. The integral of dt is t. So I'm focusing on the right side for a second. The right side is k t, and then let's put the plus c over there, our arbitrary constant for later. But the left side, oops, The left side, that integral of dy, make sure no one's waiting, it should tell me, that y is in the bottom, which means this leads to the natural log. You can't power rule this. You don't bring the y to the top, make it a -1 exponent, because then you're dividing by 0 when you integrate. So that's the natural log of the absolute value of y. Now, I need you to think realistically here. Normally, we'll say, all right, the absolute value has to be there because of the formula, but we've also argued at times we got rid of it because the numbers inside were positive. If these numbers are positives, you don't need the absolute value. And I'm not going to be plugging any numbers into this necessarily, but you can still argue that you don't need the absolute value. We can skip the absolute value since population is bigger than 0. Population is always positive. You can't have negative people. So we can just make this a little simpler. We can just say the natural log of y is equal to k, t, and then plus that arbitrary constant. But this isn't solved for y. That's the whole point of these differential equations, is to solve it for the output variable. But if you remember your pre-calculus, we can convert from one thing to another using exponents. So remember that the log base b of, what letter do I usually use here? Let's go with A equals, I'll do E to make this very, very exact, not exaggerated, very explicit. If you have the log of something equal to a number, this is the same thing. This means interchangeable, as saying B to the E is equal to A. The main point I try and stress to my pre-calc students is something that was by itself once can't be by itself again, and the base of the log is the base of the exponential side. So when you have a natural log, the base is e. So there's a little e that's assumed here. There is an e that's assumed to be there that you're going to just see in a second. So when we convert, what we will get is that e raised to the right-hand side, so k t plus c, is equal to y. And I'm just going to change sides. So we get y equals e to the kt plus c. Doing some algebra, this is the same thing. Don't worry about this part too much, as e to the kt times e to the c. I'm separating these. It's not something you would ever do normally. Normally we would take what we have and make it what we had before. But if you have like bases, you can add the exponents, kt plus c, and just make it one base. It's normally better to have this, but the reason I want to do it this way is because this e to the c is just a constant, e is just a constant, so e to the c is a constant. Let's call it a new c. So they're not going to be the same thing, but you can still just say this is equal to y equals to, and I'm not going to write it as c anymore, I'm going to write it as p sub 0 times e to the k t. So this right here, this e to the c is what I'm calling p sub 0. I just wrote it first instead of second. This is our standard exponential model when things are growing continuously. Now, if you have money in a bank account that's compounding daily or quarterly or monthly or something like that, we have those kooky or crazier formulas that we're not going to worry about because you can't get those from differential equations. This you can. This assumes that whatever we're talking about is growing constantly. And you can take any finite exponential model and turn it into a continuous exponential model like this, but we don't have time to discuss that, unfortunately. Now, what we call p sub 0 is the initial population at year 0. Now, if we're really talking about year 0, there was probably no people. So you couldn't use that as a model here. You can't have that be 0. You have to define a time at which you're starting this. So if it's the year 2020, maybe I'd say year 0 is 1920, and I'm looking at 100 years worth of growth. So the population in 1920, which was, I don't know, 40 million, 30 million, I'm guessing here. That would be the initial population that I could put here. K is the growth rate. So this is basically the percentage that we're growing based on the population of that current year. But we go from this simple differential equation, dy over dt equals ky. At first glance, you wouldn't think that that's going to lead to an exponential equation, but it does. And the reason is because the variable on the right side is not t, it's y. But this is very common. This idea that something grows proportional to how much we have is very, very, very common. When we talk population growth on a medium scale, this is how things work. Now, why do I say a medium scale? Because on a long scale, things will slow down a population because there's a limiting factor, a carrying capacity. These are common names for them. And they lead to what's known as the logistical equation, which it's a little above what I want to be solving with us in here. And I've already kind of given the idea of what this model looks like. But this right here, this y equals p sub 0 e to the kt, if you graph this, if right here is time 0, here's p sub 0, there's the population at year 0, and then it would just grow exponentially over time. So it would grow slowly at first and then start exploding eventually. So this is our exponential model versus the thing I just talked about but did not write anything. Again, that differential equation, just a little above our pay grade for being the last day of class. So not showing you the original equation, not showing you the model, but what that curve ends up doing, you still have your initial population of p sub 0. This is still time, and this is still the population. And it'll grow quicker and quicker and quicker at first, but eventually, as we get closer to what we call the carrying capacity, we slow down and we actually level off. Ultimately, millions of years later, to what we call the max population, which I think they use as L in the textbook. I like C for carrying capacity. Give me a second because I'm looking for where they had theirs. Maybe it was 380. Sorry, I know I'm wasting time. I'm looking for something. Yeah, they use the letter L. They do. Good. Couple things to note. This p sub 0, while in application we typically call it that, you could also have just called it at C. So p sub 0 could have just been written as a new C, like I was saying originally. So again, if you didn't want to write this as p sub 0, you can just call it C. And the same thing is going to be determinable. It's just that C is now the initial population. And you'll see some mathematical models write it that way. Come on, let me scroll. So we have again, these limiting factors, maybe it's the amount of space we have, maybe it's the amount of food we have, maybe we're over polluting other things, whatever it might be, but there's a reason that it flattens out and it's no longer going to just keep growing uninhibitedly. That's another name for the left blue graph. This is uninhibited growth, where nothing's going to stop this from ever just becoming infinite if you went on forever and ever and ever. I will show the differential equation. I kind of lied. I just want you to see it. So when there is a limiting factor, a carrying capacity, a maximum population, whatever you want to call it, it ends up being this as a differential equation. It's proportional, so there's a k, but to a product of two things. And it's a product of the population, which we used y before, now we're using p for population, and 1 minus the population. I'm sorry, not 1, L. If you scale the carrying capacity to 1, then it's 1, but I don't want to do it that way. That's L minus P. So L is the carrying capacity, the max population, if you will. P is the population. So this right here was the original model we had, but now we have this L minus P. What does this do? The L minus P, when your population is small, this number right here, this P would be very small, but this number would be very, very large, because this L, maybe this is 1 billion people. Let's just say the maximum population of America is 1 billion people, just arbitrary number. So when your population is really at 10, this billion minus 10 is going to be a very big number, but this P, the population of 10 people, is going to be very small. So when you multiply them together, you still have a small number, so it gives you your small growth. But as these get about halfway between the two things, these numbers are closer and closer to each other. They're no longer a small product, they're bigger, which will give us the biggest growth rate, which will give us the biggest slope. But then as time progresses, these two things kind of flip-flop. The population will become big, but the maximum minus the population will become small. So now that's going to slow us down. Again, this is what limits our growth. This right here is what limits our growth and will slow us down over time. So if you were to follow the math of that, what you end up with as an equation, and this one looks a little funkier, there was a N and a K in there. It's the maximum population divided by, and then this should be 1 plus, and then our constant, which we could call P sub 0, that's our initial population, times e to the negative RT, or negative KT, excuse me, since I used K. All right. So check that stuff out. If you just Google logistical growth, you'll probably find some really crazy stuff on it. Page 383 of your text actually kind of goes through some discussion with this, as well as I think there's something on page 222 or 223 where they introduce the idea. I might be off on the page numbers, but if you check your appendix, then you can confirm those. So if you want to look at 100 years of a population model, exponential is fine. If you want to look at 1,000 years, you got to go logistical. Maybe even at 200 years, maybe even at 150 years. If you want to talk about 10 or 20 years, you could go linear, because if you zoom in on this thing really, 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 really far, just anywhere, let me see how far this will zoom in. I might hit the maximum. Yep, I'm at the maximum. So what we're going to have to do instead is go to our calculator. So let's just make some arbitrary numbers. Let's say we had a population of 1 million. And then we're growing at a 2% rate every year, so 0.02x. I'm definitely going to need to make my own window for this one. Let's go between years 0 and 100. The y minimum, we definitely want 0. The y maximum, maybe like 10 million. So So we see our slow growth at first, and eventually it picks up because with more people, we can reproduce more, and then they can reproduce more, and they can reproduce more, and they can reproduce more. So you get your standard exponential curve. And it bends. But check this out. If I zoom in just anywhere along the curve, so that definitely looks like it's bending some. But when I zoom in more, it doesn't look as bendy. It bends just a teeny bit. You can see it's bowing just a little bit, but it looks a little more like a line. So now we're only looking at, let's just use the window. Now we're only looking from years 37 to 62. So now we're only looking at about 25 years worth of growth. So when we cut down to 25, this exponential curve could be approximated by a linear curve very well. It's not 100% accurate, but it's very accurate. If I zoom in even further, let's try and zoom in near the curve, just somewhere arbitrarily. I can't even tell that that's a non-linear curve. That looks like a line to me. And the window, I'm only looking at 6 years. So that's kind of the geometric reasoning why exponential growth, if you go to a shorter time, you can model it with linear. Or logistical growth, if I started out with a logistical curve and I zoomed in to maybe only 100 years worth, it would look exponential. You wouldn't see the slowdown effect or the tapering off. As long as I look at the first 50% of it, basically. The last half, it would look a little different. It would look more like a logarithm, which is why they call it logistical growth, because it's a combination of exponential and logistical. It's kind of like it's exponential at first and then logarithmic after. This is the same idea behind having derivatives be the rate of change of the y over the x, because whenever you go into the smallest scale possible, no matter how funky or bendy or whatever the curve is, when you zoom in enough, every single differentiable function looks like a line. It's just a matter of how far you have to zoom in. Sometimes you zoom in 1 or 2 times, sometimes you have to zoom in 5 or 6 times. Let's make our original window go from 0 to 1,000. So we're looking at 1,000 years, which would not be a great, and look, the population already maxed out really quickly, so the y minimum, let's go from 0 to 100 million. Let's see. Oh, we already hit 100 million there, so let's add another 0. And I'm still not even hitting it over there. So this is definitely just a massive explosion of population. And we're now at, what's that, 1 billion people? Just looking at 1,000 years worth of growth. Starting at 100,000 people, we're not going to end up with 1 billion people in 1,000 years for one country. That's just, it's not going to be growing this rapidly, again, because we're looking at too long of a scale. But even still, if I zoom in, instead of looking at 1,000 years, let's zoom in on the later part of the graph. Instead of zooming in on the beginning part, let's zoom in on the later part. That looks pretty linear almost. You might be able to tell it's bending a little, and if you can, then you can just zoom in one more time. And that definitely looks like a line to me. Again, any curve, if you look close enough to it, you put your nose to the board, you get your microscope out, all curves, when you're looking at, say, just a distance of 0.00000001 in any direction, they all end up being lines, which is the entire idea of us being able to come up with slope as a rate of change based on 2 points that squish into 1. Because as we squish them into 1 point, as we look at a smaller and smaller and smaller and smaller picture, as we zoom in more, everything looks like a line. So even though slopes of curves aren't constant, by zooming in to the infinitesimal changes, we can say that the slope at a point is constant, but then have functions over multiple points. And that's been the whole point of this course. Okay. So let us zoom back out on this. And let's go on to, that was 5.7. Again, just some fun, quote, fun discussions. I know I'm sick and twisted in what my definition of fun is. 6.2, partial derivatives. Now, you might say, oh, okay, well, that means you're taking a derivative of part of something. Because when we integrated by parts, we integrated part of it at one point and then the other part of it later. So are we going to do the derivative of a part now and then a derivative of another part later? No. The word partial here is drastically different than what we meant by the word part with integration by parts. Integration by parts was you had your u and your dv's, you ended up integrating to get dv, and then you integrated the vdu later to get the last bit, because you integrated it one part now, one part later. That's integration by parts. A partial derivative, the word partial means we're going to be in multiple dimensions. So these are for functions, multiple variables. There's an important word here that I'm going to go back in all caps, bold it, underline it. Partial derivatives are used for functions of multiple variables. So not implicit functions, or not implicit equations. Not implicit functions, equations, however you want to say that. Remember, implicit means that it's not solved for y, or it's not solved for z. It might say something like 3 equals x plus y. Now, that one you could solve it, but the ones that we dealt with in 3.7 or something like that, we really weren't able to solve those, so we had to use implicit differentiation, which was where when we took a derivative, if we were doing, say, d dx, whenever we took a derivative of an x, it was fine. But whenever we took a derivative of y or a z or any other letter, you had to chain rule it and throw that dy dx in there, along with the regular old derivative. Those were not written as functions explicitly. They maybe were functions, they maybe weren't. Implicit differentiation is used when it's not written out as f of whatever equals or a variable equals. So partial derivatives, partial differentiation is used when it says f of x comma y equals or z equals. So you must be told which variable to differentiate with respect to. When you do so, pretend all other variables are constants. So if I tell you to take the partial derivative with respect to x, if you see an x, you take its derivative, which would be 1, or if you see an x squared, you take its derivative, which would be 2x, etc. But if you see a y, if you saw a y, you're actually going to pretend that that y is just a 3, and its derivative would be 0. Or if you saw a y squared, you would pretend that that y squared is just a 3, and its derivative would be 0. Now, that doesn't say that all the other variables disappear. That's if they're their own terms. You can have products of x's and y's, which enables us to keep y's in that thing as we move forward. Some notation. Come on, man. Sorry, my dog is being a dog. All right, there we go. So first of all, you have to be given some f of, let's just say x comma y. Now it could be f of x comma y comma z, it could be f of a comma b comma c comma d. It can have as many variables in whatever letters you like, whatever they like. So if we're just given an f of x comma y, there are two derivatives we can do. The partial derivative with respect to x would be this. And it looks like a 2, it's not. This also looks like a really weird d. That's what you need to pretend this is, just a really weird d. It's like we took a d, but we curled it around like that. So that's just a weird d. This is the notation for a partial derivative of the function with respect to x. So x is what we would treat as a variable. All other letters, we'd act like they were 3s or 9s or 7s. But we would actually write that 3 or 9 or 7. We'd write y when we had to write it. Alternatively, there's another notation. It looks like this. So capital F and then a little x. So this little x is kind of like when we write a prime, but you can't write a prime because that doesn't tell what letter we're doing with respect to. So the lower x tells us that this is a partial derivative with respect to x. It's not a regular derivative. This has got multiple variables, and we're pretending that x is the only variable. So we're only looking at that plane is the idea there. Then we have the partial derivative with respect to y. It would look like this. Curly looking d, then your f over curly looking d, and I bet you can guess this is a y. Or you go f and then a little y. You can also do this with multiple derivatives. You can do a second derivative, a third derivative. You can take your derivative with respect to x, then with respect to x again. You can take it with respect to x, then y. You could do it with y, then x. You could do it with y and then y again. It just depends on the point of the problem, which we're not going to be able to get into that layer of detail, though. So I won't really go too far into this. Why I needed to draw the asterisks. Could have just done it this way. Higher order derivatives can be done many ways. If you had something like d squared df over dx dy, this would be the derivative with respect to x, and then the derivative with respect to y. And it's kind of weird because in one version, the first letter is first, but in the other version, it's the last letter that's first. So I'll actually show what this one would be. This would be, you've got the derivative in terms of y. So you do this first. You do your df dy, but then you take the derivative of that with respect to x. And again, my curly d's end up looking like 2s sometimes. Please know those are not 2s. There's no 2s written anywhere here. So that says you're doing the derivative with respect to y. X. Oh, I wrote those backwards. Darn it, darn it, darn it. Eraser. That one should go yx. Obviously, I said this one's y and then this one's y. That's first, that's first. So again, they kind of swap orders depending on the notation seen. So if this was something we had to use frequently, you'd have to get used to. Or if you're always going to do it this way, know that the first occurs on the right, the second occurs on the left. If you're going to do it this way, know that the first is first and the second second. The parentheses really helps go from this version to this version, though, I think. So there's the derivative with respect to y, then the derivative with respect to x. You could do the derivative with respect to x squared. I don't want those to look like 2s. So that would be fxx. You could do the derivative with respect to y squared. So that's 2 derivatives of y. That would be fyy. If you take the derivative with respect to x then y, it doesn't have to be the same thing as the derivative with respect to y then x. So what I'm saying is this thing and this thing don't have to be the same. Sometimes they are, sometimes they aren't. When they are the same, there's a cool feature about them in terms of differential calculus that we're not going to get into. So there's our notations. There's the basic ideas. Let's actually try this out. Let's do some examples. We're not going to do too many. So let's say we had, I'm going to zoom out just a little. Oh, I need a new page anyways. There we go. Okay. Example. Let's say find fx, fy, and we'll just do that for this one, for a. And let's say our original function, f of xy, is going to be equal to, let's go with x to the fifth plus y to the fourth plus x to the third times y to the second. 3 terms. First 2 terms just have a single variable. The last one has multiple variables. So I'll show both notations. Finding f sub x would be the same thing as finding curly looking df, curly looking dx. So this is what we're doing. We're pretending that anything that's not an x is a constant. This variable says this is what we're going to do our derivative rules with. If you don't see this variable, then you're dealing with a constant. The derivative of a constant is a 0. So this x to the fifth, that's normal. Everything's going to play out normally here because we're taking the derivative with respect to x. So that's going to be 5x to the fourth. But this y to the fourth, there's no x's here. So that's a constant. This is like just saying plus 10. The derivative of 10 is nothing. So I'm going to write the plus 0 here for clarity. Derivative of y to the fourth with respect to x is 0. Now, if I took it with respect to y, these would be very opposite stories, as we'll see. Plus. Now, we're taking the derivative with respect to x. So in this term, there's x's and y's. This is our variable. So this will have derivatives played out normally, but we don't need implicit differentiation. We don't have to do a product rule and an extra dy dx somewhere because this was written as a function. It was explicit, not implicit. And we were told to take a partial derivative, which is something completely different. So the x cubed, when we take that derivative, it'll be 3x squared. This y squared, this is like having an 11 here. So what's the derivative of 11x cubed? It's 11 times 3x squared. But it's not really 11, it's y squared, so just leave the y squared. So this will be 3x squared. That's the derivative of the x cubed times y squared. Again, this was a constant. We're pretending that's an 11, so the 11 has to stay there because it's not the same letter as that variable. This played very differently than the middle term because the middle term had no variables as what we're considering to be the variable in this instance. So this is really just 5x to the fourth plus 3x squared, y squared. All right. What about f sub y? What about if we find the partial derivative with respect to y? And again, geometrically, what we're doing here is only looking at the z and the y planes. So we've got a 3-dimensional image, but we're just going to take a piece of paper and lay it in a way that we're only looking at 2 of the 3 planes. Or you can imagine yourself slicing out a piece of paper from one plane. So now we're going back to this, and we're pretending that the x's are constants and the y's are variables. So the derivative of x to the fifth, well, this is a constant. The derivative of a constant is 0. Plus, this y to the fourth is now a normal acting variable. So drop the 4, decrease the exponent. So that's a plus 4y cubed. Plus, now everything's flip-flopped in this term. The x cubed, this counts as the number, and the y squared counts as our variable. So the x cubed is like having a 17. So you'd leave the 17 there, and then take the derivative of the y squared, which would be 2y. But it's not really 17. it's really x cubed. Again, just imagine yourself putting a number in place of the variables that you're not differentiating with respect to. So x cubed times 2y. We don't need the 0, the 2 can go up front, so that's 4y cubed plus 2x cubed y. These are not the same answer. Taking a derivative with respect to x is definitely not the same as doing it with respect to y. And for A, the instructions were actually supposed to be find the partial derivatives in the first. For part B, let's find fxx, fxy, fyx, and fyy. We got 4 of them to do. Now these will be based off of these two things. We don't need to go back to the original function because we're doing second derivatives. These are second derivatives, a derivative of a derivative. So we're going to go back to these two functions, but we got to know which one to use. Now remember, the second subbed letter was the first derivative to occur. So when we're doing fxx, that means we need to take this first one and then take the derivative with respect to x. When we're doing the second thing, fxy, that means we're taking f sub y and then doing the derivative with respect to x. So for this very first one, we'll start with the red one. For the second one, we're going to start with the blue one. All right, but one at a time, fxx. That would be the derivative with respect to x of f sub x. If you need your parentheses, you can use it. You don't have to, though. Again, remember that the second letter in this format is the first derivative. It's something you have to keep track of. And the alternative notation of this is d curly d f. I put the 2 in the wrong spot. Forgive me there. The 2 goes here, and that is a 2 over, and then dx squared. So we're taking the derivative of this thing with respect to x. 5x to the 4th, the derivative would be 5 times 4x cubed. Then plus, for this term, the 3x squared y squared, the 3 and the y squared act as a constant. They don't really affect anything except multiply in the end. But the derivative of the x squared is 2x. So that would be 3 times 2x times y squared. Again, the 3 and the y squared stay because they're constants. I don't just toss out the y squared because it wasn't by itself. And this would be 20x cubed plus 6xy squared. So that's the second derivative with respect to x both times. Let's do this one next, actually. We'll do this second. I'm going to do these out of order. Let me erase and emphasize that. So fy, oops, wrong thing, arg. Let's do the yx and then the xy in that order. I'm just putting them in an order that just flows a little better. The order is completely arbitrary. So fyx, so f sub yx, this is the partial derivative of f with respect to x, then with respect to y. So again, the x goes first. We just found that earlier in red. So this was fx. This was fy. So we're going to take the derivative of this thing again, but now we're going to take it with respect to y. So it's the derivative with respect to y of f sub x. That's what that's equivalent to. Or the derivative with respect to y with respect to x. taking the derivative of 5x to the fourth with respect to y, those are variables with respect to y, so it's 0. Let me erase first. 0, and plus, taking the derivative of 3x squared y squared with respect to y, now the 3x squared is the constant, so you drop the 2 out in front of the y, so that's a 2y. So we leave the 3x squared, those are our constants, and times the 2y, which is just 6x squared y. This would be our fyx, so derivative with respect to x, then with respect to y. And again, that last one was fxx, doing it with x twice. All right, what about swapping the order of the derivatives? What if this blue version right here was doing x then y? What if we do y then x? So this would be y then x. Again, just the different ways you can write it. I'm not expecting perfection with this on the last day. As I said, I'm not going to throw it on the final, but I do want you to see it because you could see this in like a 400 level economics class, potentially, if you're going that route. So now we're going to start with the derivative with respect to y. That was the right-hand letter in the subnotation, or the I wrote these two backwards, didn't I? Yeah, it doesn't matter. XY. There we go. So again, we're taking this derivative and we're going to take its derivative with respect to x. So the derivative with respect to x of 4y cubed is 0. There's no x's. Plus. Now this one's got an x. So treat the 2 and the y as constants. So 3x squared will be the derivative of that, and then everything else is just still there. So 2 times 3x squared times y, which is 6x squared y. That's the derivative with respect to y then x. These happen to be the same thing. Again, that's a cool feature that some functions have. Not all functions are supposed to have that, though. When you get into, if you were going to advanced differential calculus, you'd talk about that feature. Last but not least, fyy. The partial with respect to y, then again. So what do we start with? We start with the derivative of with respect to y. So we're starting with this guy right here, which we just did before, and now we're going to take the derivative with respect to y. First term's got a y, second term's got a y. So the derivative of 4y cubed would be 4 times 3y squared, plus the derivative of 2x cubed y, the 2 and the x cubed don't have any effect, it's just the y. The derivative of y is 1. So that's 2 times x cubed, and I will write the 1 here for detail, but then that just gives us 12y squared plus 2x cubed. That's our fyy. Derivatives with respect to a variable can still have the other variable in them. Pretty much all of these, you can see that. Just because you take a derivative with respect to x doesn't mean all the y's disappear, and vice versa. This can also be seen with a third variable, a fourth variable, a 12th variable. It doesn't matter. You can have as many variables as you need. So maybe you've got a function that's dependent on time and it's dependent on population. Maybe you're trying to model the net worth of America, and two independent variables that you could strongly base that off of are how many years have gone by and how many people there are. So that would be a function of time and population. And maybe you were only interested in how this model changes based on time changing, or maybe you're interested in only seeing how this model changes based on the population changing. Now you might say, well, Mr. Beckner, population is a function of time. Couldn't you boil that down to one variable? Yes, in theory you could, but in actual application, these could be very complex functions in which you could not compose them in an easy manner. So again, this type of differential situation, these partial derivatives, is when you're only interested in looking at a plane of a three-dimensional graph and then talking about the growth rate in that plane. And it's very hard to demonstrate drawing it up. But if you look on page 562 of your text, which it'll take me too long to pull up and make worth it. So go back and check out page 562. This is what I'm referring to. They've kind of, I'll draw it up the best I can. And please forgive me for this being terrible looking. But what they end up having is a surface. Oh man, this is going to be bad. That kind of looks like this, but then it contours. It's not just a two-dimension. This is not a circle. So with these lines, with these curves, excuse me, what I'm trying to demonstrate is that it's like the top of a bent surface. That's what I'm trying to demonstrate here very, very, very poorly. And another way to kind of help that might be to cross them as well. Ooh, that got ugly. You know what? I think I am going to pull up the text. And to show that this isn't a circle, what they do is they transpose it down to the bottom plane, and then you can see it's a circle on the bottom plane. So this red ink doesn't actually exist. It kind of, if you looked at it from a side, it would kind of have this shape. It would be bent like this. This is a side view of it. So if we took a plane, so if we just took a two-dimensional cut out of this thing, something like this, and that should be dotted. What this would do is you would end up seeing just this portion of the curve inside of that plane. And if we set these up with axes, if we call this the x-axis, this the y-axis, and then this the z-axis, if that plane is actually, let me just do that a little better so it's in the same direction. Why did I go to red? I didn't mean to do that. So here's your x, here's your y. So because this plane is moving in the same direction as x, any slope along this curve here would be df dx. That would be the partial derivative of the function with respect to x, because we're basically ignoring any change in y. We're staying on a single y value. So give me a few minutes. Log in. Chapter 6. So you'll get a better picture of what I was just trying to establish there, but I still wanted to draw it by hand. I feel like you just have to. And this is page 562, so next page. Here we go. This is what I was just putting together, just in a slightly different perspective. So here's our surface, and they do a much better job with colors and everything, being able to show the contour of the surface. You can really see that it's bending. And like I said, if you looked at it from a side view would look more like this. It kind of looks like a downward facing parabola, but it stops at this outer region. A cap to something maybe, I don't know. So they have their 3 dimensions. Instead of just x and y, in 3 dimensions, you have x, y, and z. And you can, depending on whether you're a physicist or an engineer, you might swap the x's and the y's. This is much more appropriate in my opinion because it shows torque appropriately, but we don't need to discuss torque. It's the right-hand rule for torque, how force is applied when you apply it in a circular motion where the force actually goes. And it's perpendicular to how you're applying force. Like, just imagine yourself using a screwdriver. When you screw the screwdriver clockwise, the screw goes in because you're applying force in. When you screw counterclockwise, you're unscrewing it because you're kind of applying the force outward. You're still pushing, but you get the idea. When they developed screws and screwdrivers, they went with that idea. The right-hand rule. All right, so here was the original curve. Again, they project this down. This red part down here is not really part of the function. It's just showing that if you projected it down, it would be a circle. But it doesn't look circular because of our perspective. All right, so take a piece of paper and slice this thing along, or parallel to the y-axis. So because this thing is using a specific x value, this x value of a is what this plane is representing. If you are in this plane, the x value has to be a, maybe 5, maybe 10, whatever number it is. So it's only y and z that are varying in this plane. Since only y and z are varying, any derivative in this plane would be the derivative of z with respect to y, because we're not considering x changing. We're considering x to be a constant, whatever that number is. Flip the script. I gotta take annotate off. Just scroll, there we go. Let me clear the screen. Now, this plane right here is running parallel to the x-axis, which means we're only looking at one single value of y. So this is a fixed value of y. So now with a fixed value of y, only z and x can change, so that's why it's a partial derivative of z with respect to x, because we're not letting the y change anymore. Again, there's still y values at play, though if you've got y squares or y cubes in the functions, they would still be there. But again, we're only looking at a plane of this. So again, this little blue part right here. And then if you're on this point right here, this line would have a slope of that partial derivative. If you were on this point, this line would have a slope of the other partial derivative. And again, in applications, very often people are interested in considering one variable to be constant and then see how everything else's change is affected. Maybe increasing time would cause our function to change more, be more manipulatable if we hold the population constant, or vice versa. Maybe if we look at a fixed population and just time changing, you might say, well, that would never happen. Maybe it would with a virus running around and you know, taking our population down some. Maybe that's a thing. And in economics, you could say, all right, well, one of the variables could be the price, and the other could actually be the demand, which is partially based on the price, or typically based on the price, depending on how simple or complex you're going. You could look at it as a function based on price and the number of units out there. If you only make 10 units of something, and it's actually, you know, something people want, high demand, you could probably make the price whatever you want, in theory. So you could say, all right, if we hold the number of items fixed, how would the price adjustment be? Or vice versa, if you hold the price fixed, how do we need to adjust the number of units made based on some other variable? Because in our class, we've looked at functions for these models when we've modeled stuff in very simple terms as just functions of one variable. Very often, real-world models are dependent on several variables. I have seen models where there were over 100 dependent variables. Now, that was absurd, but it exists. If you wanted to try and mathematically model, the health of a person, the life expectancy of a person, let's say, I couldn't count on 100,000 people's fingers the number of variables at play, probably. I mean, you could create the most insane mathematical model on life expectancy with so many variables, it would just be absurd, because human nature, the variables are all over the place. Where did you come from? Who are your parents? What genes do you have? What did you do on day 5 of your life? What did you do on day 100 of your life? Do you drive? What do you eat? What do you not eat? Do you exercise? Did you go to college? Do you have a high school degree? Do you have no degree? What's your income? What's your hair look like? What's your skin color? What's your weight? How many bones have you broken? How many ulcers have you had? I mean, good Lord, I could create the most insane model if I actually had 5 lifetimes to do it. But that's not the point of this. We're just having fun discussing crazy extenuating circumstances for models to go crazy. But again, for us, we like to break things down 1 variable, maybe 2 if we have to, keep it simple and say, all right, well, if in the real world this should be modeled with 50 variables, maybe our 1 variable model is only going to talk about 5 years or 10 years or 100 years. And then you can study that model and you can look at what happens as things continue to change and maybe try and invoke something else in your model. Maybe try and throw in another variable and see how it interacts with everything else, with success, with failure, anything. For every good model I've made, I probably made 900 bad models before it. Okay. So we're going to go ahead and call it there. We got enough of these ideas down from what's happened. Oh, I have annotated on, that's why. I was wondering why I couldn't get back to my notes. So again, the final exam will only cover up to and including what we did last class. So nothing from 5.7, nothing from 6.2. I'm going to open up the homeworks for those of you who are curious and want to try that stuff out. But I'm not going to make it mandatory. I will not count it as a grade. It's not going to hurt you. It's not going to help you. They're just if you really like this stuff and want to try it out. If you have no interest in it, if you have no time, then focus on the review material. Focus on 4, 6, 5, 3, and 6, 1 for the newest stuff. Those are homeworks that are due. 5.7, 6.2, not required for homework. Okay. So when is your final? Thursday. If you try to take it Friday, you're not going to be able to. If you email me to take it Friday, you're not going to be able to. You have to take it Thursday. Do not, please, please, please do not get this confused. There will be no exceptions to this unless you have a medical note or something like that. Of course, in which case grade changes have to be done. But we can always do something like that in post, but I'd need documentation in those scenarios. So let's just try and keep this normal. You all have done a great job, staying pace all semester. You've done a great job with the tests. It has been a pleasure to teach you in the way that I've had to teach you. I mean, obviously, I wish we could have done this face-to-face, but we got to keep everybody safe. So I've tried to emphasize knowledge absorption more than anything else. I've given you these kind of breaks with the tests. I could have been much less lenient on them. Even though, like I said, one of the leniencies that taking a second test, hardly anyone even used it, if only once the whole semester. And moving forward, I'm not going to be doing that anymore. I've already said that to myself for my fall classes. I'm just going to do 1 test and only 1 test. All right. And thank you as well. So again, it's been an honor. It's been a pleasure. Please email me if you have any questions. Remember, no class Thursday, because just in case you need those 2 hours to take the test. And by the way, if I didn't say it, the test is 2 hours. So it's 120 minutes. It'll be about 25 to 30, yeah, about 25 questions. Maybe 30. So I'm thinking 26, 27, but no more than 30. And there'll be shorter questions. There'll be a couple of longer questions, but I will keep, if I go 30, you'll have a decent amount of shorter ones. You will be able to do this in 2 hours, I guarantee you. I give this test in an hour and a half in class, so 2 hours on your own should be more than fine. All right, I'm glad I'm seeing some people say that you appreciate this class. That's awesome. Again, I hope that you can find some way to use simple ideas from this course in your real life if possible. Outside of that, when you go and take economics classes and business classes, you'll see some ideas that you've seen before. But change. This world does nothing but change. Calculus is the study of change. They're really, 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 really tied together. And if you are if you wanted to study some of this stuff in more greater detail, you'd probably benefit from going back and taking Pre-Calc 2, because it's kind of a dead end right here to get into the crazier concepts of calculus without doing trigonometry. So if you like this stuff, if you want to learn more, I would suggest that you go back and take Pre-Calc 2, or just look up some information on the internet. But you can just go check out a regular calculus book, regular calculus materials, and get more heavy into these differential equations, go more into the three-dimensional concepts. You can look up those economic applications on your own that we kind of touched and went with. But yeah, all right, I'll stop rambling now. Have a good one. Take care. Email me with any questions. Final should be up Thursday, 12:01 a.m. It's due 11:59 p.m. Grades will be posted Friday morning. You may not see them till Friday afternoon or some point over the weekend, or at worst Monday morning if SIS is weird, which they don't tell us when they actually show. But I will be putting grades in Friday morning. Take care. Have a great summer. Stay safe. Make good decisions. I love you all.
Professor?
Yes.
Hey, I have one question. Tim Dodge.
Hey, what's up?
I accidentally thought the test 3 was due on
I don't want you to say this stuff in the recording. I saw your email before class.
Okay.
I'm going to email you right after this.
Yeah, I confused the test 3 with the final exam. So, all right, thank you.
All right, thank you. Yeah, check your email right after class.
Yes, sir. Thank you.
You're welcome.